This content is AI generated for informational purposes only and should not be directly used for clinical decision-making.
Hello, and welcome back to the Neurosurgery Hub podcast. I'm Dr. Aris, Senior Attending Neurosurgeon.
And I'm Dr. Alara, Research Fellow. Today we're looking at a fascinating new study from the Journal of Clinical Neuroscience, published in 2026, titled Real-Time Intraoperative Depth Estimation in Transsphenoidal Surgery Using Deep Learning, a Feasibility Study.
This is a topic that hits home for anyone who spends significant time in the endonasal corridor. When we talk about endoscopic endonasal and transcranial approaches, we are usually dealing with complex pathologies, pituitary adenomas, craniopharyngiomas, chordomas, or meningiomas. Alara, as a fellow, you're often the one holding the scope or watching the monitor. What's the biggest technical hurdle we face with the current standard?
It's definitely the loss of the third dimension. As the paper points out, the video feed provided by endoscopes is generally two-dimensional. While we train our brains to compensate using monocular cues, that 2D limitation can significantly hinder depth perception. It makes fine movements around critical neurovascular structures just that much more taxing.
Exactly. We've seen 3D endoscopes come onto the market, but they require specialized, often bulky hardware and specific glasses. This study takes a different route. They are looking at generating three-dimensional imaging without the need for those special endoscopes. Instead, they're leveraging deep learning.
Right. The core of this research is a feasibility study on real-time intraoperative depth estimation. Essentially, they want to take that standard 2D feed we already have in every OR and use a deep learning model to calculate depth on the fly.
The clinical appeal here is enhanced intraoperative orientation. If we can use deep learning to reconstruct the 3D geometry of the surgical field from a single lens, we gain the benefits of depth perception without the overhead of 3D hardware. Why is that specifically important for the pathologies mentioned, the adenomas and chordomas?
Well, the paper emphasizes that these approaches are used for the resection of various pathological lesions where precision is paramount. In transsphenoidal surgery, the margins are slim. If the deep learning model can provide real-time depth estimation, it could theoretically help the surgeon better understand the distance to the carotid artery or the optic chiasm, even when using a standard 2D scope.
It's about bridging that gap. The study frames this as a feasibility study, which is an important distinction for our residents and students listening. They aren't saying this is the gold standard yet. They are asking, is it possible to do this accurately in real time?
And the real-time aspect is the key. In neurosurgery, a delay of even a few seconds in processing the video feed would make the technology useless, or worse, dangerous. The deep learning algorithms have to process the frames fast enough to keep up with a surgeon's movements during the resection.
What I find particularly interesting is the potential for enhanced intraoperative orientation without changing our workflow. If we don't need special endoscopes, we don't have to worry about the ergonomic shifts or the cost barriers that usually come with 3D tech.
Precisely. The paper suggests that by using deep learning to generate this 3D imaging, we can potentially mitigate the risks associated with hindered depth perception. It's about taking the data already present in the 2D video feed and extracting more information from it than the human eye can see alone.
It really speaks to where the field is going, moving away from just better hardware and toward smarter software. For the medical students listening, this is a perfect example of how computer science is integrating with surgical technique to solve a classic problem like depth perception in endoscopic endonasal approaches.
It's a great study that sets the stage for how we might view the surgical field in the very near future. Using deep learning for intraoperative orientation could soon be a standard part of our toolkit for meningiomas and other skull-based tumors.
A lean, software-based solution for a hardware-heavy problem. Thank you for walking us through that, Alara.
My pleasure.
And thank you all for tuning in to the Neurosurgery Hub podcast. We'll see you in the next episode.